Hello, everyone. Welcome back to the AAS YouTube channel. And this one is a module in the AAS Author Series. And I'm super pleased to have Mike Montgomery with us today. Hi, Mike.
Howdy. How are you doing?
Good. I'm hanging in there, all things considered.
Super.
Okay. We'll hit our first 100 degree Fahrenheit day tomorrow. I'm here in Phoenix, in case anybody is interested. And then we'll peak out at about 105 on Wednesday, next Wednesday, and then it'll cool down a little bit. So we're already in the triple digits here.
Well, we've hit 90 here in Texas, but we still are down in the mid to low 60s at night sometimes, which is just fantastic weather.
Yeah, that's lovely, lovely, especially if the humidity isn't up yet. So.
Yeah, no, today is not a humid day. Yesterday was a very humid day, so it just varies.
Yeah, that time of year, spring. Spring 2020. So why don't you tell people a little bit where you're at and what you like to do for research and that kind of stuff.
Well, sure. Yeah, my name is Mike Montgomery. I'm a research scientist in the astronomy department at UT Austin. I've been here for about 16 years now. I did the rather unconventional thing of being an undergraduate here.
Ooh, wow.
Then went off and got a physics, a master's in physics from Princeton. Decided I really didn't want to do string theory and wanted to get back into astronomy. And so I decided to actually come back to UT to do that. And I worked with Don Winget. And then I did a 2-year postdoc at the Institute of Astronomy in Vienna with Michael Breger, who works on Delta Scuti stars. And then I did a 3.5-year postdoc with Douglas Goff in Cambridge, working on all sorts of pulsations, not helioseismology, but seismology of other stars. And like I say, I've been back here since 2004. Wow. So I've kind of been around, and I've obviously focused on the pulsations of stars, but I've also always been interested and done research on the interiors of stars. So just physical processes like phase separation, carbon-oxygen phase separation, the effects it has, diffusion in white dwarf envelopes, convection in white dwarf envelopes, and of course, these processes in other stars. And I first met you, Frank, at the very first Mesa Summer School, which I can't quite remember, 2011, 2010? 2012, okay. It was that very first one. And of course, after that, we collaborated on the second Mesa instrument paper.
We did?
Which I'm still quite proud of because, it's great to be involved with a nice project like Mesa, which is doing so much for so many in the stellar evolution field. So that's kind of my history. And I've been at UT. I also teach the FRI program, the astronomy part. FRI stands for Freshman Research Initiative, and we take 30 freshmen and get them into research projects the second semester, their first year, and the first semester, their second year, so that they can get some research experience.
These would be grads or undergrads?
Oh, these are undergrads.
Undergrads, okay.
That's why it's called the Freshman Research Initiative, and it's an experimental program, and it's spreading to other places.
Cool.
And needless to say, it does take a good amount of time because getting freshmen involved in research is not the simplest thing there is. But the great thing we're doing is we're replacing some of the awful freshman physics labs with actual research experience. So we have a very low bar in order to do better than what we're replacing. It's the way because I took those labs. And they weren't good. Yeah, they weren't good. And they make you think,
not good.
This is really research. And so, as you know, in astronomy, even if we don't take new data, there's so much data out there to look at that it's not hard to find projects for students.
Absolutely. Cool.
So anyway, that's kind of where I'm at.
That's awesome. Let's go ahead and get to your lovely recent paper. So I'm going to do a screen share, people. So we're going to cover limits on mode coherence in pulsating DA white dwarfs due to a non-static convection zone. Mike, take it away.
Sure, thanks. And I just want to make sure I am brief enough that it all fits in. I don't know the right way of thinking about this. I first thought about mode coherence when I read about solar pulsations, and they take data over time periods of years and they average it all together and they get nice Lorentzian peaks and they can actually measure the width of those peaks. And those peaks are really telling you something about the damping rates of those modes. Now, those are special pulsations. They're stochastically excited, so they decay linearly, and they're stochastically bumped up in amplitude. So you're really getting that linear decay in the width of the mode. Now, classical pulsators aren't stochastically excited. They're linearly driven, and so there's not necessarily this nice relationship between the width of the mode and any damping or driving rates. Because you can have a non-zero driving rate and the mode comes up to a finite amplitude, but then some nonlinear dampening happens and you get a constant amplitude.
Yeah.
And when you FT that, you get a very narrow peak that has nothing to do with the driving or damping rate. So in white dwarfs, we never had the chance to look at this before because you could only take data for a couple of weeks. And most you could do a 6-week run, 6-week run. And that's with ground-based data where all the telescopes, I was a member of the Whole Earth Telescope, it's a consortium, and it's great, but you have 12 different instruments looking at the star with 12 different instrumental characteristics, and you have weather. And you roll all that together, and it's really hard to get a pulse shape that, or a peak shape in your FT that's narrow. In fact, we never got a resolution to where we could see any modes were wider than 1/T of our observations.
Wow, okay.
But when you move to space, all of a sudden those things go away. You can get with Kepler to K2, which has just been a huge boon for our field. You get 90 days of data or so, 80 to 90 days of data, pretty much continuous, 95% duty cycle, all the same instrument, very well understood systematics. And it turned out we actually could see that some modes were wider than others.
Cool.
And so that was the motivation for this. So I hate to do it right off, Frank, but would it be possible to put up that other plot?
Sure, absolutely.
Because that's what motivated us. J.J. Hermes has been leading, he and Keaton Bell have been leading, I would say, the data analysis of pulsating white dwarfs in the Kepler data set. Of course, many, many people are involved. But JJ published this, he's at Boston University now, published a paper on 27 DAVs observed with Kepler, and that number is going to increase up into the 70s or 80s in the next year as the remainder of the data is published. But here's what he saw. You look at some modes in some stars. The upper left-hand corner is a 907 second mode, and you can see it's just sort of a forest of little peaks.
Yeah.
And the width of that's quite wide. The horizontal axis is microhertz. And then in the same star, a 411 second mode has a very, very narrow peak. And by the way, the red curves are Lorentzians.
Yes.
And you can, you see the same thing in 3 other stars here, that the high period modes, we sort of have taken to calling these modeled modes because they seem to have a modeled appearance.
Okay.
And that the high period modes are modeled and the low period modes aren't. And JJ, I mean, I would love to take credit for, you know, thinking of all the ideas here, but JJ is the one who said, I wonder if this could have something to do with convection. Because, you know, the long period modes, the models say they should propagate closer to the surface. Maybe they're hitting the convection zone. Maybe this is what's messing them up.
Right.
And so I was very excited about this idea, but I as a theorist, or, you know, I do a lot of theory. I do some observations, but mainly theory. I said, but, you know, if the timescales don't match, they don't match. And so the odds of this working are maybe 50%, maybe less. But lo and behold, perhaps we should go back to my paper now. It turns out that when we ran preliminary models, that the timescales matched up very well. So if you could put our paper up and maybe go to the second page, figure 1. So that's the one on the left there. And what's plotted here is for those 27 DAVs in Kepler, we, you know, each star has many, many periods. Right. So all the periods of all those stars are plotted. So some stars have 10 circles up here. And for all the periods, that's the horizontal axis. We've plotted how wide they are, and that's the vertical axis. And you can see above 800 seconds that's where the modes that are wide are, and below 800 seconds is where the narrow modes are. And we took the cutoff to be around 0.3 microhertz, just because that produced a nice demarcation between the 2 sets of modes.
How many stars are on this?
27.
27.
27.
Okay.
And we used spectroscopically determined temperatures for those stars, so that modes that came from stars that were hot, we made blue, more than 11,500 count, and for the others, we did red.
Got it. Well, something's certainly happening around 800, 700 seconds.
Absolutely. And also around 11,500 degrees, right? Because that seems to, I mean, the two populations, red versus blue, it doesn't do a bad job of separating those two.
Yeah, there's a little bit of, red on the left and blue on the right, but in general, yeah.
Oh yeah, no. Well, this is a theory, so things don't work perfectly, but it seems to capture the ensemble characteristics of things.
Agreed.
Yeah. Okay. So this was very promising. This looked good. But then what we wanted to do is check and see if it really worked quantitatively with models.
Okay.
So if we could just slide over to figure 2.
Ooh, classic.
Yeah, here's a propagation diagram for a generic white dwarf model. I think it was around 11,500 degrees. And this is in terms of log of envelope mass. So 0 is the center of the star, and 15 is, or 16 is actually pretty much the photosphere. And you can see the convection zone is located out in the outer parts. The Brunt-Weissler frequency is the gray curve, and the Lamb frequency is the green curve. The Brunt-Weissler frequency is the buoyancy frequency, so it's the thing that really determines the properties of the G modes. And the Lamb frequency is also important as far as determining where the reflections occur. And so you can see I've labeled the blue curve, the blue dashed line, P short, is a mode that propagates out to about 10 to the minus 11 and hits the Lamb frequency and then bounces back. And the red curve is a lower frequency mode, and it propagates out to the base of the convection zone, hits that and bounces back. So those are two qualitatively different behaviors, because as the star pulsates, these are actually not that small amplitude pulsations. The photometric variations are 5 to 10% often.
Ooh, okay.
And so the change in temperature is many hundred Kelvin, if not 1,000 Kelvin sometimes.
Yeah.
And the convection zone is extremely sensitive to changes in temperature. The mass in the convection zone, according to MLT, can go like the effective temperature to the minus 90th power. So a few percent change in temperature can mean a 50% change in the convection zone. So imagine that right boundary that the mode is hitting for the base of the convection zone moving back and forth to the left and right. As the blue line bounces, it doesn't see any of that because the Lamb frequency isn't moving.
Yeah, it's too far.
But the red curve sees, it's as if it's a vibrating string whose length is changing. So you would think that maybe it has trouble being a mode. You know what I mean? It has trouble setting up a nice standing wave. Correct. So then this crossover period is the period, it's the maximum period that just barely hits the convection zone or just barely doesn't. That is a function of temperature, because as the models get cooler, the convection zone gets deeper.
Yep.
And it turns out that now one other thing that we didn't talk about here, but is in JJ's paper, is just in general for white dwarfs, the hot ones around 12,500 degrees have short period oscillations, say 200 to 300 seconds. And as they cool off, the pulsations get longer in period. So in other words, the hot stars have thin convection zones and very short period modes, so they don't get anywhere near the convection zone. As you go to cooler stars, the convection zone gets deeper and the modes get longer period, which means they propagate farther out in the envelope too. And it turns out, according to the models, that this crossover region is around 11,500 degrees for what you would expect MLT to be. And when I say expect MLT to be, I mean, take, for instance, the 3D convection simulations of Tremblay et al. And say, what do they give you for a 0.6 solar mass white dwarf at 11,500 degrees? And the answer is about an alpha of 0.76. That's what we put in our models, and it about works. So it seemed like the proof of concept worked. In fact, when I initially ran the models, we got that between 800 and 900 seconds would be the crossover region. So I thought that was spectacularly good. For not tweaking anything, that was pretty darn good.
Yeah.
let's see. So if you just go down one figure, this is an illustration for the same model or a similar model, just the outer part of the convection zone,
Okay.
that since each star can have many modes in it, the short period modes can avoid hitting the convection zone, where the long period modes will hit the convection zone. And so it naturally leads to an explanation where some modes could be wide modeled and some could be narrow, as we see in the actual data. So that's the only point of this figure, is to show that it's not a crazy idea. In other words, there's not just unstable stars and stable stars. It's that one star can have both stable and less stable modes in it. And when I say stable, I don't mean, linearly unstable like driven. I mean less coherent modes in it than other modes. So just because a star has modes that aren't very coherent in it doesn't mean it can't have a very coherent mode in it if it has a short period.
Right, and there's definitely a little difference there between L equal 1 and L equal 2 Lamb curves.
Exactly. So L equal 2, that's the dashed line there. So even the blue curve, the upper blue dashed line, if it were in L equal 2 mode, it would propagate all the way out to that dashed green curve and almost hit the base of the convection zone. So a prediction of this model, which is unverified as of yet, is that the maximum very coherent period you would expect in stars is smaller if it's L equal 2 than if it is L equal 1.
That's a testable one, I think, yeah?
I think it is, but identifying L's is not the easiest thing to do.
Fair enough, fair enough.
JJ was able to identify, or rather, he was able to give plausible identifications to about 40% of the modes in those 27 DAVs. If they were triplets, it was natural to assume. And if there were other triplets that were spaced about as far apart as you would expect for an L equal 1 G mode spacing, then they were called L equal 1 modes.
Okay.
So using a few different criteria, none of which are necessarily watertight, but are definitely give you a good guess. So yeah, this is testable. So I'm really hopeful when JJ comes out with the new set of 80 that we're able to test some of these ideas more.
Cool.
All right, well, let's see. Maybe we should go on to figure 4. So I was reminded by my collaborators that it's important to differentiate things not just in terms of color, but in terms of shape, because many people have some form of color blindness. Plus, if you print it on black and white. The result, however, is what I call the Lucky Charms plot. I don't think I've ever done a plot with this many happy symbols on it before. But the point of this plot is we wanted to see how well do we do with this hypothesis. So let's take that set of 207 modes. Again, 40% of them had an ID. So the ones that were L equals 1 we treated, the ones that were L equals 2 we treated, and then of course the greater number of which didn't have an ID, we also wanted to treat. And so what we did, this was a complicated plot. For all 27 DAVs, we have good spectroscopic values of T effective and log G. Using those values, we could compute a convection zone depth for all those 27 stars.
Okay.
And then we could say, okay, well, this star has these 5 periods in it. With this T effective, log G, and assumption of Mexican link parameter, do each of those fall in the right category? In other words, the 500-second mode in the data is a very narrow mode. Is it predicted to not hit the convection zone? And if that was true, then we put a filled symbol on the plot.
Okay.
If we got it wrong, it was a unfilled symbol. So like the hollow triangle you see there in the middle.
Okay.
And so the L equal 1 modes are denoted one way with the triangles. The L equals 2 are the diamonds, and the unidentifieds were assumed to be L equal 1 for the purpose of the test because that's more conservative. If they were L equals 2, then obviously everything to the right of about 600 seconds would be filled in if it were wide. Yeah. So we get an accuracy of prediction rate of about 81% doing this. So a given star, we typically get 80 or 90% of the modes right, and for the whole ensemble, we get about 80% right. So we don't do perfectly. I would really like to know, for instance, how some of the stars have a mode at 1200 seconds.
Right.
It isn't modeled. It's apparently there and doing just fine. I have been told by some of my collaborators that we need to reanalyze this data and make sure that we are doing exactly what we want when we fit a Lorentzian to a forest of peaks.
Yeah.
Keaton Bell especially, he's been working in the field of red giant pulsations, where they were looking at line shapes, and their data were similar to this. And he thinks that if we did a more sophisticated Bayesian approach, that frankly, some of those narrow long period modes might go away.
Okay.
So,
Yeah.
but anyway, that's work for the future. Again, I'm trying to really establish this as a plausibility argument. And
Okay.
to me, it seems to do that. So let's see. So I think then if we go to the next figure, the point of this figure, I don't know about other fields of stars, but in the white dwarf field, we have the impression that most of our modes are L=1 modes. In other words, L=1 modes suffer less geometric cancellation, so they should have larger amplitudes.
Yeah.
An L=2 mode with the same intrinsic amplitude in the star, the same local temperature perturbation, should have a smaller observed amplitude because there's more cancellation between positive and negative, high temperature and low temperature. And as you go to L=3 and 4, it's even more severe.
Right.
But we've always had the impression in the white dwarf field that there's even fewer L=2 modes than would be accounted for by just an amplitude reduction due to geometric effects. So I wanted to look here and say, can we say anything about this here? And honestly, we can't say anything definitive because 60% of the modes are unidentified. If the percent of L=1 and 2 in the identified modes are the same as in the unidentified modes, then we probably could say something, but we can't make that assumption a priori. But what we did do is say, let's look at the distribution of L=1 modes as a function of their amplitude. And this is a KDE, you know, it's like a histogram,
Right.
kernel density estimation. And so you see that our L=1 modes tend to peak around 1 part per thousand, 1.2 parts per thousand. Our L=2s tend to peak around 0.7 or 0.8 parts per thousand, and at lower amplitudes, as you would kind of expect. What we then did is we took the L=1 curve and said, imagine that we had exactly the same distribution for L=2s. We know how to scale the amplitudes down if they were L=2s. It's about a factor of 0.7 or something. And so we did that and we got the green curve.
Okay.
And so if you were to just believe these numbers at face value, you'd say, well, if you rescaled the L=1 to the L=2, you'd have many more L=2s than we actually see in the stars. Because the green curve, the scaled predicted number of L=2s, is much bigger than the pink curve.
Yep.
But of course, when you've got 60% floating around that are unidentified, a slight asymmetry there could do something here.
Yeah.
But still, I find this as a plausibility argument. And so I'm hoping, you know, in the future years that this would, that we could nail this down better.
Is this something Tess could do something with?
Maybe. You know, obviously Tess can look at the brighter white dwarfs which pulsate, but it can get good data on some of them. So I'm waiting with bated breath for the new sample from JJ to see what's buried in there. And obviously in the back of my mind, I'm thinking, well, yeah, and this mechanism we have, it's more injurious to the L=2 modes. Maybe it would reduce their amplitudes even more over what they would be due to this lack of coherence, and therefore it would cause there to be less L=2 than other things. So it, you know, it all kind of goes in the same direction. One interesting thing that I noticed here is I also did the experiment for take the L=1s and pretend they were L=3s and 4s. What would you expect to see?
Okay.
And the answer is below your detection threshold.
Yeah.
it's really severe going to L equal 3 and 4. I mean, I knew that, but frankly, I thought that from space with Kepler, 90 days of data, we could do something, and it turns out, no, you just don't see them.
Yeah, yeah.
Too bad. All right, well, so the next part of the paper kind of deals with the physics of how I think a mode should interact with the convection zone.
Okay.
And I should say that this work goes back to when I was a postdoc with Douglas Goff. And I remember talking to him about these problems, and he was always very interested. And we could just never quite think of the right way of doing it. But it appealed to me and interested me because I didn't see how these could be modes, if you know what I mean. It really bothered me that these things really weren't modes. Of course, I've learned since then that that's not a big deal at all. You know, that even atoms can have resonances that aren't totally stable, but they might as well be modes for all intents and purposes.
Okay.
So it took me a while to figure out the right way to treat this. If your convection zone is changing depth,
yeah,
as the modes pulsate. So due to the fact that there's 5 or 10 pulsation modes in the star, the surface temperature is going up and down. Yanxin Wu and Peter Goldreich showed that you could treat the convection zone quasi-statically, that it should respond with its structure to the instantaneous temperature on a time scale of a second or less. It's really fast.
Okay.
The convective turnover time scale is like tenths of seconds, just super fast. So mechanically, it's in equilibrium.
Yeah.
But the fact that the temperature is going up and down makes the depth of the convection zone go up and down. And so a mode which is hitting it sometimes has a farther distance to travel than it does at other times.
Right.
And this causes it to either pick up or lose a little bit of phase. It's as if you were reflecting off one end of a string where the string length was changing with time.
Yep.
And so that was the first effect that I thought of several years ago. But then thinking of it more physically, I realized, well, it's not just that effect, but the fact that the boundary is moving, you're going to get a Doppler shift. And, you know, then I was thinking more to myself, imagine you have a wall and you're bouncing a sound wave off of it.
Oh, I see. Yeah, yeah.
Then you get a Doppler shift from the velocity of the wall.
Yeah.
Now, actually making this experiment isn't so hard, but obviously it works great with police radar, right? They can tell how fast you're going.
Exactly.
And I even talked to a friend of mine who works at Applied Research Labs on the ionosphere, and he says, yes, the Earth's ionosphere changes depth, and it's not physically moving, it's just that these atoms are becoming ionized than they weren't before. And he says, oh yeah, we measure the velocity of that all the time by just bouncing radio waves off of it.
Yeah.
So the idea seems sound. Let's put it that way. But here, you know, we're never in as convenient a limit because, you know, radio waves are fast. You're getting millions of cycles. Here, everything's changing. The time rate of change of this is the same as the time rate of change of the modes. Everything's happening on hundreds of seconds. So you're not in a nice asymptotic regime necessarily that you would be for other kinds of things. Well, anyway, well, that's illustrated in these two diagrams here. The one on the left, the mode just has to propagate a little farther, and so there's a phase offset. The mode on the right, it bounces off a wall, and it doesn't go any farther, but it gets Doppler shifted, so its frequency is slightly higher, and since its frequency is higher, its spatial wavelength is slightly different. So as it bounces all the way down and back again, it'll have an extra bit of phase.
Yep.
And it turns out that the Doppler effect almost always is the bigger effect.
All right.
Mainly because when you increase the frequency, that makes the wavelength of the mode different all the way down and all the way back, and so it's a cumulative. It's an accumulation of phase.
Okay.
The only time in which it would be about the same is if the mode were an n=1 overtone mode. So you just had one wavelength out to the surface.
Yeah.
And you could argue, does this even apply in that limit? Because, you know, you're not really in an asymptotic regime where you can use the WKB approximation to talk about the wave. But anyway, so it turns out that that's the dominant effect. So let's see where we're going. I imagine that stuff like this had been worked out somewhere before in acoustics, probably.
Yeah.
But I wasn't able to find any. I wasn't able to find any references for it. So
work it out.
Yeah, exactly. And again, the math's not hard. It's the physical assumptions that you need to make. Basically, if you come down to equation 12, I think you just up a little bit. Equation 12, and just shows that delta phi is, if this is the region in which the mode propagates, center to surface,
okay.
We're going in from the outer propagation region a little bit and saying, how does the phase of this out to its outer turning point change with time? Because as the convection zone comes in and goes out a little bit, that number is going to change. And so delta phi is the amount of phase it accumulates between this point R naught and the outer turning point, and it changes with time. It just turns out that the change in frequency is related to d by dt of that phase change. And it's because you can think of the mode as reflecting off a surface of constant mode phase, and that surface of constant mode phase is moving in and out because the outer region is moving in and out.
Right.
The reason we had to phrase it this way, though, is because the asymptotic form for the velocity actually goes to 0 right at the reflection point, because that's where your approximation breaks down, that I can think of a local wave just propagating. And so we can't apply the Doppler shift right at the boundary. We have to integrate in from the boundary. What's that?
Yeah, because it's 0 right at the boundary.
Exactly. So, in theory, whenever you get 0 or infinity from an answer, you need to go back and look at the problem differently. Yeah. So that's what we did, and we came up with this formula, which seems to have nice properties and is well justified. So that's the one we went with for calculating the change in frequency, and then for each mode, it's easy to calculate the extra phase that it comes back with. And in equation 14 in the right column, that's what we've done, is we've added up the extra phase now from surface to center back to the surface again. That's how off in phase it should be. So what I'm saying is, if delta phi in that expression were 0, then it would be completely coherent, and the change in amplitude dA dt would be 0. But the fact that it's not means that the amplitude is going to be changed, is going to change a little bit. It's going to be negative, because essentially you're adding up two waves that aren't quite in phase, and so you get less amplitude than you would if they added completely coherently.
Mm-hmm.
And then formula 15, we just averaged over the possible delta phis. One thing I want to mention is that this is a nonlinear effect, but it's nonlinear in the background state. So I'm just assuming that the star is changing due to the sum of a whole bunch of modes.
Mm-hmm.
But this formula will be true even for a mode with very small amplitude. It's going to see these same delta phi variations because the other modes are causing the convection zone to move in and out. So it's not nonlinear in its amplitude, it's nonlinear in the sum of all the amplitudes of all the modes.
Okay.
So it's a little of both. So in other words, a large amplitude mode can prevent a small amplitude mode from growing, because the small amplitude mode still sees this damping due to this effect. All right.
I'm with you.
And then I'm not going to say much about it, but I used the Mesa Stellar Evolution code for the models.
Yeah, let's not say much about that.
What's that?
Yeah, let's not say much about that.
Yeah, no, because that could go on for hours. But basically, I simulated the effect that when you have a pulsation mode and it makes the surface hot, that doesn't change the entire model, it only changes the surface layers. And so that's captured by this plot here, where the really important curve is delta n squared over n squared. And you can see as you come in from the surface, it decays to 0. And there were some technical details here, but they're not important. Okay. And that's because obviously, if your mode is pulsating, it has a large amplitude on the outside of the star and a very small amplitude on the inside of the star. If I were really doing this carefully, I would have used the eigenfunctions themselves to perturb the structure of the model and then use that.
Okay.
But that's starting to get to be a harder calculation, and I wanted this to be a little more exploratory. All right, cool. So if you go on, I suppose, to figure 9, and again, there's technical details, but I feel we should leave them out. I wanted to compare the damping rates that one might expect from this with the driving rates, which also you might expect in these stars, or at least these models. And I used the Wu and Goldreich theory for convective driving with data from her thesis and a couple of other publications. And that's the red line on this curve.
Mm-hmm.
And so on the left figure, you can see modes are only driven up to about 400 or 500 seconds. And that's just because it's a 12,000 degrees white dwarf and they don't have modes. The driving is for lower period modes. As they get cooler, the driving extends up to higher periods. And the damping rates I threw on there, assuming that the total temperature excursions of the surface of the star were 50 Kelvin. So it's 12,000 plus or minus 50 Kelvin.
Okay.
And you can see that the damping is negligible for the low period modes where you would expect it to be driven. So this shouldn't affect the driving of the hot stars at all. Of course, modulo retreating this and getting a different answer. But I don't think it will affect those. Now, the opposite case is the 11,000 degree model, which predicts that modes all the way down to 1400 seconds, all the way up to 1400 seconds should be driven. And here in this case, I've taken a larger amplitude of 100 Kelvin because these stars just have larger amplitudes. We observe that. And frankly, 100 Kelvin's pretty conservative. They're often 200 Kelvin. And so then you see that the damping rates are quite significant for modes above 900 seconds for L equal 1. And so this would predict that you wouldn't. It's confusing what this predicts, however. This predicts that you would not expect to see large amplitude modes above 900 seconds. If they had small enough amplitudes, perhaps they could survive. But it should definitely dampen the very long amplitude, long period modes.
Yes. Okay, I'm with you.
All right, cool. And then we might want to skip the next figure. It was an exploration of parameter space. I wanted to see what do L equals 2 and 3 modes do too. And it turns out that they do kind of the same thing. Let's see, yeah, that's figure 10. They do kind of and there's 4 panels to it if you go up. They do kind of the same thing, just at shorter periods. So
yes,
the lower left, the upper left hand shows the 12,000 degree model, and the dashed blue curve is the driving, and you see the driving goes up to 500 seconds for L equals 1, but it only goes up to about 350 seconds for L equals 2, and only about 250 for L equals 3. And so the expected excited range changes and the damping changes, and they both seem to scale in similar ways. And so as you go cooler, let's look at the 11,000 degrees, so the lower left hand of that sequence of 4 plots. For the L equal 1, you see that large driving in the dashed blue going out, and the cutoff where the damping intersects around 700 seconds. But for L equals 2, the orange curves, that intersection's around 400, and for L equals 3s, that's around 250.
Right.
And so everything just scales back. And so, like I was saying earlier, a prediction of this model is you wouldn't expect to see long period L equals 2 modes. So it'll be interesting to see in the data if we are able to identify modes that are, say, 800 or 900 seconds long, and we really think they're L equals 2, because that would be a challenge to this. Unless, of course, you know, it's a hot star. If it's somehow or other a 12,000 degree star, then not only is the damping a problem, but our driving is also not right. And so, but definitely this would seem to de-emphasize, you don't expect to see the long period L equal 2s due to this mechanism. And then the very last plot, figure 11, just says, well, you know, this was all motivated by this mode width thing. Wouldn't it be neat if we could actually predict the mode widths? And
Okay.
I've thought an awful lot about this, and the answer is it's very difficult to come up with a nice criterion because, again, if you have a driven mode, you know, it comes up from the infinitesimal level, gets larger, and then some nonlinear effect kicks in and limits the amplitude. That should make a nice narrow mode in the FT. If you were to modulate the damping, if the damping went up and down, then the amplitude would go up and down. That would produce a width.
Right.
If that's correct, then you need to understand why is there a modulation in the damping, and then you have to come up with a whole theory for why it would change. So this, in the spirit of simple-minded phenomenology,
Right.
our Doppler shift is producing a change in frequency. You know, let's just interpret that change in frequency as a width in the Fourier transform.
Okay.
If you do that, then you get these curves. So the L equal 1 width goes up steeply as a function of period around 800 seconds. Again, this is for an 11,500 model with log G of 8 and the expected mixing length parameter. And the amount of temperature variations is plus or minus 200 Kelvin, which again is about typical for middle of the instability strip. And the L equal 2 curve you see goes up around 450 seconds and says, good golly, all the L equal 2 modes should be very wide indeed. I'm not saying I even believe this, it's just a phenomenological plot that shows it has something to do. Things get big at the right place. But is this the right metric with which to, that really is most directly connected to the mode width? I don't think so, but I haven't thought of what a better criterion would be.
Okay.
So that's kind of where we leave this. I realize I've taken a long time, so perhaps this is too long.
No.
Let me just backtrack and give an introduction I should have. White dwarfs are, of course, just interesting on their own, and everybody should love them. But they're also interesting to other astronomers because they can give you ages of stellar populations. They were the first objects to give us an age of the galactic disk of about 10 gigayears, back when people were saying it was still 20 gigayears. Right. And that number hasn't changed very much in the intervening 30 years. But they're also really interesting for many other things. A lot of them have debris disks around them, which we think are ground up asteroids or planetesimal material. Yeah. And we see the metals in the surfaces. Yeah. Those metals should settle out in a time scale of weeks. And so the fact that we see them means there's continuous accretion occurring. If you want to get the abundances of the stuff, then you need to know how fast it settles out. And calcium doesn't necessarily settle as fast as magnesium. So you need to have a model of diffusion. It turns out that those diffusion timescales depend most strongly on the depth of the convection zones of these white dwarfs. The deeper they are, the slower they are. But the more disparate they are from magnesium to calcium, for instance, too. So you get the wrong ratio if you don't do it right. So all of this work is aimed at, can we understand white dwarf convection zones better? Can we measure their depths better and therefore derive other things from them better? So that's kind of the bird's eye view. And also some white dwarfs observationally have incredibly stable pulsations. There's a DAV G117B15A, which has a measured P dot of about 4 times 10 to the minus 15 seconds per second. And you might worry, oh my God, look what he's shown here with the lack of coherence of modes. How can that possibly be? Well, it's a 215 second mode. And it's a very hot star. So it has everything going in its favor. So this work is completely consistent with there being extremely stable modes in the hot pulsators. It says maybe you better worry a little bit for the cool pulsators, but if you had a 200-second mode in them, you still might be okay. So it doesn't mean you can't use the coolest white dwarfs that are pulsating for extreme stability work, but people haven't done that because they are so uncertain with their properties for the high period modes that people have just not touched them.
Right. Well, it sounds like a good avenue for the future as the field moves on a bit.
Yeah, so people have looked for planets around orbiting or around white dwarfs in terms of O-C, orbital reflex motion time delays. And with G117 B15A, we haven't found anything, but you could rule out Jupiter at Jupiter's distance, for instance, which not many current studies can do, because it's only the close-in stuff that you get enough cycles on to be able to say things. So white dwarfs occupy an interesting region of parameter space. Just because we haven't found things doesn't mean we haven't ruled out things that are important. You know what I mean?
Absolutely. Integration times there. Cool. Very cool. All right. Thank you, Mike. I appreciate you taking the time and walking us through the paper and leading us a little bit where the future is going to lie in this area of research. And for those who are interested or would like to talk, go ahead and get in touch with Mike via email. We will not be putting his email in the YouTube description below or saying it here. But if you're in the game, you'll know how to find him. And so, yeah, that'd be cool. All right. Thanks. And we'll see you later, everyone.
All right. Thanks.
Thanks, Mike.